This is a video for MEI Core Pure Mathematics, second order differential equations 1, homogeneous equations, 1.1 auxiliary equation method for first order differential equations. We're going to start by considering the vocabulary of differential equations which we're going to use throughout this sequence of videos. We're actually going to be looking at second order linear differential equations with constant coefficients. Let's pull those pieces apart. Well, first of all, the order is the highest derivative, and the highest derivative we've got here is the second derivative, d2y by dx squared, so it's second order. It's linear because anything involving y or its derivatives has a power of 1. And constant coefficients, a, b, and c, are self-explanatory. Finally, we need to understand the terms homogeneous and non-homogeneous. This function on the right-hand side, well, if that is just 0 on the right-hand side, we say that the equation is homogeneous, and if that's non-zero, it's non-homogeneous. So before we use what we call the auxiliary equation method to solve second-order equations, we're going to look at it in the context of a first-order differential equation. We've seen this differential equation here in a previous sequence of videos and determined that the general solution is of this form, y is equal to ae to the minus kx. If you're unsure about this, either look back to your textbook or at the previous sequence of videos on first order differential equations. Okay, let's have a look at this example then. It's a first order linear differential equation. It's homogeneous because the right-hand side is 0. And I know from the previous slide that it's going to have a solution of the form a e to the kx. I've dropped the minus sign out here. It's just a general constant times x, and k could be positive or negative. Now if I substitute that into this thing here, well, I know that dy by dx from that is going to be equal to a k e to the kx. And so putting that into that differential equation, I'm going to get 3 lots of a k e to the kx plus 2 lots of a e to the kx is equal to 0. Now, provided a e to the kx is not equal to 0, this equation just simplifies down to 3k plus 2 equals 0. And this equation we call the auxiliary equation. Now if we solve that, that gives me that k is equal to minus 2/3. And so the general solution for that differential equation is going to be y is equal to a e to the minus 2/3 x. So there it is written up neatly for you. There's the original differential equation. Using this as the form of the general solution, I can substitute that into the differential equation to give me this as the auxiliary equation, and the solution to this gives me the value that I use in the general solution here. So in summary then, here's our general form for this differential equation. The auxiliary equation is very quick to form. This value here, m, will allow me to determine the general solution, and there indeed is the solution to the auxiliary equation. And so this gives me a general solution a to the mx, which in this case will be a e to the minus b over a x. This idea works for first order differential equations and can be extended for second order differential equations, and we'll look at that in a separate video. The next video is 1.2, the auxiliary equation method for second order differential equations.